Hi, welcome back. Today we're going to be continuing our discussion about quantum error correction, and specifically we'll be focusing on how we go beyond the bit flip code, which is what we discussed last time, to talk about how to implement full single qubit error correction. And specifically, we're going to do this by using a Shor code. So, because the language surrounding quantum error correction is a little bit different than the language usually used around quantum computing, I wanted to spend a little bit more time reviewing what we covered last time, perhaps from a slightly different perspective, before continuing on to talk about how to take the bit flip code, which we discussed last time, and transform that into a phase flip code. Once we have the phase flip code in place, then what we're going to be able to do is we're going to be able to concatenate this with the bit flip code to come up with a code, i.e. the Shor code, that can resist both a bit and a phase flip. Then we're going to show that being able to tolerate a bit and a phase flip ends up giving us the ability to tolerate any error that we can think of on a single qubit in a quantum computer. So that's the way that we're going to be going. So now let's start with the definition of what we would like to do. So to begin with, recall that the whole idea of quantum error correction is that we begin with particular quantum states, and then, which we call code words, for example, 0 and 1 for a single qubit, and what we do is we map these in to code spaces that are all logically equivalent. So in the case of the bit flip error, this is ideally mapped to 0, 0, 0 and 1, 1, 1. Now, we consider any quantum state that's distance 1 away in terms of the errors that we're considering, in this case bit flips, to also be in the same class. So, for example, we would also include 1, 0, 0 as being equivalent to 0, and similarly, we would consider 0, 1, 1 as being equivalent to 1. And this is the idea that what we want to do is we want to basically extend our quantum state, which previously we could think of as a single point, to now an entire equivalence class over vectors. And once we've done this, provided these two sets are disjoint, then what we're going to be able to do is take an arbitrary example, figure out that, yes, we do have a bit flip, and then transform that back to the ideal code word. And this process, quantum error correction, is going to allow us to maintain a long-lived memory in a quantum computer despite having noisy operations. So the idea behind this is that we'd like to be able to define a projector onto the different spaces that we end up having inside of this code. So just to give you a bit of an idea, right? Say we take a look at the ideal code words, right? We have 0, 0 and 1, 1, 1. These are considered to be error-free. Now, there's two other classes, 1, 0, 0, and 0, 1, 1, 0, 1, 0, 1, 0, 1, and, of course, 0, 0, 1, 1, 1, 0. This has this class has one. These classes have one error, and the position of the error differs in each of them. First one is the leftmost qubit. This is the middle one, and this one is the rightmost qubit. And so we're going to define these different classes in the following way. Okay, well, actually, sorry. What we're going to do is imagine that we have our initial state, psi, over here. And psi, we can envision as being a state that would end up following from our 1-bit code by putting in A00 plus B111. And then we put this through some error process. And then what pops out the other side is the state that we're going to call psi. So first thing is that we could trivially end up writing psi as the identity times psi. And just rewriting the identity matrix, we can, using the fact that, for example, let's look at the 2-bit identity or 1-bit identity matrix. That's just this, which, if we express that in Dirac notation, is just 0, 0 plus 1, 1. Okay? So we can use the exact same decomposition, but I'm going to rewrite it subtly differently. I'm going to rewrite this definition of the identity as being the following. Plus 0, 0, 1. Oh, and plus dot dot dot. And all of this is going to be multiplied by, of course, psi. All right, so we've got this, and note what I've got here. This can be thought of as a projection matrix that will take a vector and project it down into this error-free section. So we can envision a projector that projects onto this being P0 hat. To be clear, if we could somehow magically apply this projector P0 to psi, then what we would end up getting is we'd end up getting some state coming back out of this, which would be of the form A00 plus B111. So this is an example of an error-free state, and this projector finds the component of the state that we get in the direction of this error-free subspace, or the projection of this state onto the error-free subspace. Okay, so that is that one. Now we've got a whole bunch of errors over here. I'm going to call this projector over here P10, and similarly to how this was associated with this class, P10 will be associated with this one, the projector P11 will be associated with this one, and P12 will project onto that error. Okay, so for example, if we ended up applying P1 hat to psi, then we would end up getting some state of the form C, or P10, say, C001 plus D110. And in this case, if we can tell that through some protocol we've applied the projector onto this particular airspace, then all we have to do is take this component and we can correct it by flipping that bit. Okay, so this is the idea basically behind quantum error correction, is that we begin by discretizing the errors that we end up having, and then what we do is, after we find out what class of errors we end up getting, we apply a correction operation in order to fix them. Okay, so that's basically what we want to do, and we're going to actually implement this ultimately by through a trick involving the Hadamard test. But in order to do this, what we need to do is we need to find a way of projecting onto these spaces. So projecting onto one of these spaces, there's a trivial way that obviously, we've all kind of taken a look at, which is just measuring, right? So if I started with psi and I did the following circuit and I just measured every quantum bit, then with some probability I would end up getting 0, 0. Some probability I would get 1, 1. Some probability I'll start getting error states like 0, 0, 1, where this qubit, for example, might be flipped. Unfortunately, what if our initial state, before we put it through this error channel over here, was of the form A0 logical plus B1 logical, what we would end up getting out, even in the ideal case, is we'd end up getting out 0, 0, 0, which does not, or which is equal to 0 logical, which does not correspond to the state that we had before the error. So what we need to do is we cannot just directly measure. We have to find some clever way of projecting our vector down onto one of these classes, figuring out which class it is, and then working backwards. All right. So one of the clues that we end up getting follows from the Pauli decomposition, as I showed you last time. So using a Pauli decomposition, we can actually write the projector onto, say, the no error space as 1/4 I plus z, z, I plus z, I, z plus I, z, z. And recall here that there's implicit tensor products between each of these. So when I write it like this, just always assume that there's tensor products between everything, because explicitly drawing out the tensor products is a serious pain for many of these examples. So that's basically it. So we can end up having a projection operator of this form. The next thing that's worth noting is that for every projection operator, we end up having p0 squared equals p0. Now you can go through and verify this, but this is actually kind of obvious geometrically. For example, if we had an arbitrary vector with two components, x and y over here, and the vector was pointed out this way, the projection of this vector psi onto x over here we could envision being formed as having a projector px acting on psi, where in this case px would be equal to just x. So in this case, this would just end up being x and the inner product of x and psi. Okay, so this is just straightforward linear algebra. However, if we try to project it again, px squared psi, this is the same thing as projecting the x vector onto the x vector. Well, that projection is trivial. That is just equal to x psi. Because if we take this component down here and project it back onto itself, well, nothing changes. And that's the reason why, for every projection operator like this, the square of it is always equal to itself. But what this ends up meaning is because the square is equal to itself, right, we have that every matrix of this form can always be written in the following way, through an eigenvalue decomposition, as ud u dagger, where this over here is a diagonal matrix, and both of these are unitary. All right, so every Hermitian operator, like a projection operator, can always be written in this particular form. Okay, fantastic. So because this is diagonal, what we have is that p squared equals p ends up implying that u d u dagger squared, which is equal to u d squared u dagger, is equal to u d u dagger, implies that d squared is equal to d. Okay, And because D is a diagonal matrix, what this ends up meaning is that the eigenvalues, which are the diagonal elements of this, like D0, 0 over here, D1, 1, so on and so forth, those eigenvalues have to be equal to either 0 or 1, because those are the only two values, when squared, end up equaling themselves. So we know that the eigenvalues are 0 and 1. Okay, let's assume that we have a +1 eigenvector of P naught hat. What does that mean? Well, if we've got a +1 eigenvector of P naught hat, let's call it, I don't know, phi, then P naught hat phi is equal to P naught hat, or sorry, is equal to phi, which is exactly this case over here. So geometrically speaking, what we're saying by that is that this vector is oriented in the same direction as this projector. And in the case of the of this over here, what that means is that P naught, which again is equal to the projector onto the code space, which is given by 0, 0, 0 plus 1, 1, 1, 1, 1, 1. What this means is that our vector is phi is in the span of these two vectors. It's some linear combination of these valid code words. Okay, so that's what it ends up meaning to be a +1 eigenvalue of it. So if it's a +1 in the +1 eigenvalue, i.e. it's a valid code word from this perspective, then what we know is that from this operator over here, it also has to be a +1 eigenvector of this, this, and this. Why do we know that? Well, the reason why is because each of these operators has norm 1. And you can see that because they're the tensor product of Pauli operators, and every Pauli operator is unitary. So, therefore, every unitary matrix has norm 1. So therefore, each of these is norm 1. So no matter what, their expectation value can never be greater than 1, i.e. all of their eigenvalues have to be at most 1. So what that means, and actually it could be 1 or -1. So what that means is in order for us to attain a +1 eigenvector, when this thing is acting on a state phi, P naught phi is equal to phi, and that's equal to 1/4 identity phi plus ZI phi plus ZI phi plus IZZ phi. Okay, the only way that this can end up equaling phi is if the coefficient of this is 1, coefficient of that is 1, and the coefficient of that is 1. Therefore, in order for the vector to end up being in the span over here of all the valid code words, it must also simultaneously be a 0 eigenvector of these 3 unitary objects. So that's what we're going to do. What we're going to do is we're going to try to enact a projection into this valid space by measuring whether or not we're in the +1 or -1 eigenspace of each of these 3 operators. By the way, only 2 are actually necessary. 3 is overkill, but for pedagogical reasons, I'll put 3 in here. The reason why is that if 2 of them are valid, you can actually argue that the third one has to be 1. So we don't need to actually technically worry about the third one, but I'll keep it there just to keep things simple. Okay, so the way that we end up doing this again is we end up projecting ourselves onto the +1 eigenspace, or actually in general, but it could also be the -1 eigenspace of, say, I, Z, Z. And the way that we're going to do this is we're going to note that, again, I, Z, Z squared is equal to identity. Okay, and from this, last time what we did is we used the Hadamard test in order to show that if we end up beginning with the state 0, applying a Hadamard transform, doing a controlled U-gate, applying a Hadamard transform over here, and beginning with a state psi, what we end up getting is we end up getting back out that if P plus projects onto the span of all eigenvectors with +1 eigenvalue, and eigenvectors of this guy over here. Which means that if we had, say I had, plus sub 0 and plus sub 1 as being our positive eigenvectors, what that means is P plus would be equal to, could be written as plus sub 0 plus sub 1. Okay, so very explicitly, this is the matrix that would implement that projection. Okay, cool. So then we've got this, and P minus is going to be the operator that projects onto, does the exact same thing, but it will project onto the eigenvectors with -1 eigenvalue. All right, if that's the case, then the Hadamard transform, or the Hadamard test for this, will map 0 and psi over to 0 P plus acting on psi plus 1 P minus acting on psi. So in this particular case, where the operator squared is equal to identity, what measuring this bit at the top over here will result in the bottom vector being transformed into either its positive or its negative component. So what that allows us to do is that allows us to determine whether we're in the +1 or -1 eigenspace of each of these operators. And in turn, if we measured each of them in this way, and we got +1, +1, and +1 over here, then in that case we would know that we've applied the projection onto this error-free state. And then we would end up having a vector in the end, which is corrected. So that's great. Let's envision let's look at what the circuit would be for this. So if we ended up having a state over here, which is like some error operator acting on A000 plus B111, then the Hadamard transform circuit, or Hadamard test circuit, I should say, is going to be of the form a 3 H's, then a controlled, just want to make sure that I'm matching the order right, controlled Z, Z here, then Z, Z here, and then Z, Z there. Okay, where that goes down here. So we can view these as 3 distinct Hadamard tests. By the way, as I said before, only 2 of these are actually needed, but I put 3 in just so that way it's matching the 3 terms in the Pauli decomposition. Okay, H, and now we're going to measure them out. Okay, and let's say we end up getting A, B, and C. As mentioned before, if A, B, and C are all equal to 0, then we're in a +1 eigenspace of I, Z, 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 I, Z, and Z, Z, I. Okay, which implies in eigenspace +1 of P naught hat. Okay, so that means that we've projected onto the error-free state, which is awesome. But if you think about it, we don't necessarily always have to measure 0. We could end up measuring other values. And so then the question is, if we measure other values, what ends up happening? Well, we can go through the math and take a look at the rest of our subsets of errors. It turns out that when we do a Pauli decomposition of the rest of them, the bit flip case where we end up having the rightmost bit flipped can be written in the form P10 hat, which again is equal to the projector onto the space 0, 0, 1, 0, 0, 1, plus 1, 1, 0, 1, 1, 0, which again corresponds to 1-bit flip error in both of our code words in the rightmost bit. This can actually be written as something that looks almost identical to what we had before, but with different signs on it. We end up getting minus Z, Z, I, plus Z, I, Z, minus I, Z, Z. So what we do in this case is we project onto this particular space when we're in the -1 eigenspace of these two operators, but the +1 eigenspace of that. So that is basically what we end up doing. Sorry, actually, I think I might have copied this down wrong. Yeah, this is plus ZZI minus ZIZ minus IZZ. Yes, exactly. This makes much more sense. Now, we can take a look at this and actually develop some intuition for this. Because if we take a look at these two code words, right? The two code words are 0 and 1 in both of those locations. So if we were to apply this first term, ZZI, to it, what would we end up getting? Well, here we would get +1 by applying poly Z on 0. We would get +1 by applying poly Z on 0. And we would get, well, +1 by applying identity on 1. When we multiply these three together from the tensor products, we end up getting +1. Similarly over here, by multiplying this by ZZI, we get -1 from Z on the first one, -1 from Z on the second one, and 1 from Z on the third one, which, of course, gives us +1. So we could end up seeing that ZZI, ideally on this space, would end up giving us +1. Similarly, if we apply ZIZ on these, we would end up seeing that this will end up giving us -1. And this also will give us -1. So by taking a look at these signs, another way of thinking about this projection is that by measuring these particular signs, we can estimate the parity. So these two are consistent. That's what the +1 eigenvalue ends up meaning of this. Whereas the -1 means that those two values are inconsistent. So in particular, say we take a look at this one. This and that are opposite bits, and that's bit values. So that what that means is it's got parity 1, meaning that it corresponds to a -1 eigenvalue of this. So just by looking at that, we can actually identify which bit is incorrect. We know the first two are the same, but from this, we know that the first one is different from the third one. So that's why it's got a -1 eigenvalue. And in turn, you can see why this is redundant information in this case, because we can actually identify which bit is flipped only from this and that. So, great. That's the projector onto P10. The projector onto P11, similarly, which is the error in the middle one, which is 0, 1, 0, 0, 1, 0, plus 1, 0, 1, 1, 0, 1. That thing's what I tried to write before, which is identity minus ZZI plus ZIZ minus IZZ. Okay? And similarly, we can go and write the error on the last remaining bit, and that is, unsurprisingly, 1/4 I minus ZZI minus ZIZ plus IZZ. And we see that this is exactly what we expect, because this is the bit that's been flipped for that error class. And so we would expect a -1 sign on all the terms involving that qubit. So, great. All right, so now from this, we can actually also take a look at what values of A, B, and C we would expect from our circuit to correspond to this class of errors. From this, we end up seeing that this ends up occurring when A equals 0, B equals 1, and C equals 1. This corresponds to A equals 1, B equals 0, C equals 1. And this, of course, corresponds to A equals 1, B equals 1, C equals 0. So we can actually draw, then, the correction circuit up here in the following way. First class is going to be the form 0, 1, 1. Classical information flows into here. Oh, and by the way, this over here means 0 controlled. So the fire the gate classically when that bit is 0. If that occurs, then the rightmost bit is flipped. And so we will apply the correction, which is an X gate to it. Then if we see this sequence over here, then we know the middle gate is flipped, or middle bit is flipped, so apply the correction there. And finally, what we have is the last sequence is this. Which we can fix by flipping the bit that had an error in it, which was the leftmost bit. So, kind of like the teleportation circuit, irrespective of what single qubit has been flipped in the process, what we can do, like for example, I could put an X gate anywhere on these. I could put one here, I could put one there. In all of those cases corresponding to an X error, this circuit would identify which bit has been flipped, correct the error, and the result would still be, at the end, A00 plus B11 a 1 for all A and B. So that's the cool bit, is that by measuring the parities between each of these individual quantum bits, and then determining whether or not these parities are backtracking in order to figure out where the error was from those parities, which are also known as syndromes, we can then figure out what bit to correct without giving us any information about whether we have this code word or that code word. And that's vital for making sure that the state remain an appropriate superposition of the two. So that's how we get around the fact that measurement actually has back action on our states in quantum computing, and how we can correct errors without explicitly or without directly measuring the quantum state. Instead, we indirectly measure it through these parity operations and the Hadamard test. So that is how we end up doing it. Now, let's talk about generalizing this to the case of a phase flip code. So, in this particular case, what we have is, imagine we had our quantum state encoded, and this is the standard encoding circuit for starting with an unencoded quantum bit and encoding it inside the error correcting code for the bit flip code would be the following. Be that and that. Okay? So this over here would end up giving us, of course, A000 plus B111, which is A0L plus B1L. All right, great. So now let's assume something slightly different ends up happening. Let's assume what we end up doing is we end up having this preparation, and we put it through the following gate, Z over here. Then what we have is we have A0 logical plus B1 logical. And tracking that through, it turns out what we end up getting is we end up getting A0 logical minus B1 logical. Now, because this is in the support of P0, if we tried to do the bit flip code in order to correct this, we would end up just mapping that back to exactly the same thing. We would end up getting that this is which is not equal to our input, which was 0 logical plus B1 logical. Okay, so we can see that this Z error actually ends up causing substantial damage to our quantum state that isn't corrected by the bit flip code. However, we can change this. And the way that we change this is actually really kind of stupid in a way. What we do is we note that a phase flip actually is very, very similar to a bit flip. So, for example, let's take a look at the following states. Let's say we take a look at H0, which I'm going to call plus for this discussion, and H1, which I'm going to call minus. All right, so if these are our two states, what ends up happening if I end up applying Z8 to the H to the plus state, which is equal to Z plus? Well, ZH0 is equal to H squared ZH0, which is equal to HZH0, which is equal to H1, which is equal to minus. So you can see that Z flips between these two. So Z acts like X on plus and minus. Similarly, what we have is if we take X acting on plus then going through the exact same argument, that's the same thing as x acting on Hadamard 0, which is h squared xh 0, which is the same thing as h z 0, which is plus. Similarly, going through the exact same reasoning on the minus state, we get the exact same thing, but we end up getting that this is hz1, which is equal to minus minus. So this implies that x acts like z on plus and minus. So if we change our encoding to be an encoding in terms of plus and minus, then actually our code, our phase flip code can reduce to a bit flip code in a different basis. So in particular, what I mean by that is we have our 0 bit, and now we're going to encode this in our phase flip code in the following way. We're going to encode that as plus plus plus, and 1 we're going to encode as minus minus minus. Okay, the reason why is that if we have and this is equal to 0 logical, and that's equal to 1 logical in our case. And for example, if we have zi acting on 0 logical, then this ends up giving us a minus plus plus. So this is the exact same as it looks just like a bit flip. So we've used this in order to transform the phase flips, i.e. the Z gate applied to a particular quantum bit, to end up looking like a bit flip. So to give you an idea, of course, about how the encoding circuit would work for that, is basically it ends up working exactly the same as what we would have before. We can take an arbitrary quantum state and we can transform it into this code by doing a pair of controlled NOT gates down here, and then Hadamard transforming. The result coming back out. And what we end up getting when we do the algebra, and assume that each of these starts at 0, we end up seeing that the Hadamard transforms will transform 0 into 1 and 1 into minus. The Hadamard transforms will transform 0 into plus and 1 into minus. So this will end up giving us a plus 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 b minus 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 as required. And that is, of course, equal to a 0 logical for this code plus b1 logical for this code. All right, fantastic. So that's basically how it all works. Once we've encoded, then everything ends up looking exactly this, like we ended up doing for the decoding, except what we're going to do for the phase flip code is we're going to take all of these z's over here, and we're going to all replace them with x's. Okay, and all these x's we're going to replace with z's, because both of them fill pretty much exactly the same role in the this other basis. So that's how we end up making a circuit that can detect and correct Z errors. So, i.e., if we put a random, for this case, a random Z gate here at this location, after doing this transformation, we would actually be able to correct that error within the phase flip code. Okay, cool. So we've got two cases built up here. We've got the case where we've done a bit flip and the case where we've done a phase flip. But these two are just like kind of points in terms of the errors that we can correct. Ideally, we'd like to be able to correct any error whatsoever using a quantum error correcting code. So the way that we're going to end up doing this in general is actually by concatenating the bit flip with a phase flip code. And by nesting them together, we're going to come up with a code that can actually detect and correct both a phase flip and a bit flip at the price of requiring 9 rather than 3 quantum bits. So the way that we do this, and the first person to come up with this was Peter Shor. And this is known as a Shor code. So the Shor code ends up working as follows. What it does is it maps 0 to 0, 0, 0 plus 1, 1, 1 tensor 0, 0, 0 plus 1, 1, 1 tensor 0, 0, 0 plus 1, 1, 1, all divided by 2 square root 2. Okay. Now, this over here I'm going to write just in shorthand as the following. I'm going to write that as power tensor 3 over 2 root 2, just so I don't have to write this over and over and over again. Okay. Now, there's actually some structure to this that you can see. If we ended up writing let's define 0 logical, let's call it 0 up here, to be equal to 0, 0, 0, and 1 logical 0 is equal to 1, 1, 1. Then this mapping can be viewed as a state in the following form. It will end up looking like 0, 0L plus 1, 0L tensor 3, 2 root 2. But this over here, we can write as just being plus 0 logical tensor 3, which we can end up writing as plus 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 logical 0. Yeah. So, and this I'm going to define to be the actual logical state, 0L. So what I'm saying here basically is that we can view this as being a phase flip code, where remember this was the code word for 0 in the phase flip code, built on top of the bit flip code over here, which shows up inside there. So that's how the Shor code ends up concatenating the two. And actually, this is even more clear when you take a look at the encoding circuit for encoding a quantum bit inside the Shor code. So let's say we're provided a state A0 plus B1, and we want to protect it by storing it inside the Shor code. The way that we would do this is we would begin by preparing 3 quantum bits in the phase code. Okay, and remember the phase code encoding circuit ends up looking like following. H over here. But now what we've done is we've just done the phase code encoding, and what we need to do is we need to now put the bit flip encoding in. And we're going to do that by taking each of these tensor factors over here and now redundantly encoding them in the bit flip code. And we'll do that by using the bit flip code here. in going through the math, it's very straightforward to see that the resulting 9-qubit state that we get out the other side is A0 logical plus B1 logical, where again these logical bits are logical states are of this form. Oh, I guess I forgot to mention what 1 logical is equal to. This is equal to, of course, 0, 0, 0 minus 1, 1, 1 tensor 3 over 2 root 2. Okay, cool. So this is how we end up building the Shor code out of this. And so let's take a look at how the Shor code ends up working. Okay? So let's say what we have is we have a bit flip in first qubit. So that would be an example of something like we have this encoded circuit, and then we would apply a X gate up here. Okay? So if we've got a bit flip in the first qubit, then what that's going to do is that's going to map 0 logical to 1, 0, 0 plus 0, 1, 1 tensor 0, 0, 0 plus 1, 1, 1 tensor 2 divided by, of course, 2 root 2. Great. So now, let's imagine that we try to measure the parities using exactly the same trick that we did before. So if we measure whether we're in a +1 or -1 eigenspace of z tensor I, here we would end up getting -1 for those two bits and -1 over there as well. Similarly, if we ended up measuring z tensor I tensor z over here, we would end up getting -1 because this bit is flipped relative to that one. And from these two pieces of information, we can look at this and determine that this was the bit that was flipped. And in turn, then we would just apply X on this top bit as a correction in order to fix it. So we can project onto those two by doing the Hadamard test, just like we would do before. So the way that this would end up going through is we would have our 9-qubit code over here, and what we would do is we would measure Z controlled on say this one and controlled on that one, and we would repeat this process for all the other pairs. And that's how we would detect the presence of a bit flip at any one of these locations. All right, and then once we've done that, we can go through and we can correct that particular error. Okay, so that is how the code ends up working. It can detect the error and correct it. And while I assumed that the error happened in the first quantum bit, you can end up seeing by symmetry, because the code can correct this on the first bit, it should be able to correct this similarly on the second, third, fourth, so on and so forth. So the Shor code is capable of detecting and correcting bit flip errors. Now, let's take a look at phase flip errors. So phase flip error is going to, again, map 0 logical to 0, 0, 0, minus 1, 1, 1. And here I'm assuming that we apply a z to this, which is why we get a minus sign there. Tensored with 0, 0, 0 plus 1, 1, 1 squared divided by 2 root 2. And this is 1, and 1 logical ends up mapping to okay, great. And so now what we want to do is we want to be able to compare the phases of these two logical groups over here and determine whether or not this sign is consistent with its neighbors. And the way that we can do this is we can measure the parity of the operator x1, x2, x3, x4, x5, x6, and x4, x5, x6, x7, x8, x9. Okay, and the reason why we end up doing that is because what we want to do is we want to compare the phase, which we can measure by measuring the x operators, because that's logically the same thing as a bit flip inside this code, or sorry, it's the same thing as the z operator within a bit flip code. We want to compare block 1 and block 2, where this is block 1, and the first tensor factor over here, I'll explicitly write this out this time, 0, 0, 0 plus 1, 1, 1. The second tensor factor that we're comparing the parity up against is this one. So for example, if we end up applying xxx to 0, 0, 0 minus 1, 1, 1, then what we end up getting is that's the same thing as 1, 1, 1 minus 0, 0, 0. And that's equal to minus 0, 0, 0 minus 1, 1, 1. Okay? So by applying 3 x's, or by taking a look at whether we're in the positive, oh, and of course, the xxx acting on 0, 0, 0, similarly, ends up giving us just 0, 0, 0 plus 1, 1, 1. So, projecting ourselves onto the plus 1 or minus 1 eigenstate of xxx ends up projecting us onto a system that has either the minus sign or the plus sign, respectively, for those coordinates. So this, over here, will end up checking the parity, i.e. whether those two end up agreeing. So in the event that we have a bit flip, or phase flip over here, this operation would end up yielding minus 1 here, but plus 1 there, because the phase of this is consistent between those two. So the product that we end up getting will be plus 1. So we can end up doing this, again, using the same Hadamard test mechanic, except now things are going to be a little more complicated. The stabilizer that we're going to be measuring, which is like this string of Pauli operators, is going to be of the following form. It will look like this. Okay, and then the next one will end up going like that over here, and it'll be controlled by the next one over there. Okay, that I guess would be a Hadamard, 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 Hadamard. And then based on, this will feed into measurements, and then based on the outcomes of these measurements, just like we had before, we will propose which of these individual blocks has been monkeyed with, and we'll fix that by applying a logical Z operation to it, which we can do by applying Z, Z, Z to that block. Okay, so that is how the Shor code works, and this ends up implying by the same symmetry argument that this can correct against one arbitrary phase flip. Further, because these operations actually commute with these Z operations over here, the order that we do the measurement doesn't matter, and this implies that we can correct against both errors. So what this means is we've got the ability within this code to correct against one phase flip and one bit flip. However, we can't do more than one of each. So this actually gives us the ability to correct against an arbitrary error. Okay, this fact isn't actually super duper obvious, but it ends up coming in from some of the exact same Pauli operator arguments that we had before. So let's assume that our error that we start with a quantum state psi, and we feed this through some error operator E, and we end up getting some state psi tilde popping out the other side. Okay? Now we're going to assume that the error operator will end up taking the form for a 9-qubit state. Something like the following. It'll be like E1, E2, going all the way down to E9. So what I'm doing is I'm assuming that each of these error operators are uncorrelated. So any errors that end up popping up are on each of the qubits individually, all right? Which is a big assumption, but it's necessary in order to show that we can protect against an arbitrary error acting on a single qubit. So once we've made this assumption, we can end up using a Pauli decomposition to say that any matrix E can be written in the form E0 identity plus E1 X plus E2 Y plus E3 Z. Okay, that's cool, but recall that Zx is equal to Iy. So therefore, there exist coefficients in general such that we could always end up writing this, instead of y, as writing this as E1 x plus Zx E2 plus E3 Z. So what this ends up saying is that an arbitrary error that's described by a linear operator in this case can be written as a linear combination of no error, one bit flip, a bit plus phase flip, and a phase flip. Okay? So if we have a channel like this, then, and only one error actually ends up happening, then what we'll end up getting is that our quantum error correction circuit over here will end up taking psi tilde, and it'll map this to a projection of psi onto one of these error spaces, corresponding to no errors, one error, or an X error and a Z error, okay? So depending on the measurements that we end up getting out of our syndrome qubits, that'll end up determining which of these spaces that we project it into. So the measurement, we'll end up discretizing the errors that we end up getting. So rather than having a continuum of errors, we're actually just going to get a single discrete error coming back out. And that's kind of the magic of quantum error correction. It gives a way of taking this continuum of errors that we would expect to see and allows us to project it onto a single error. And that comes from just the Pauli decomposition. A final note that I'd like to mention is that here I ended up assuming that our error is just a single one of these operators. And this actually isn't going to be sufficient to be able to describe a general error channel. If we have an arbitrary error channel, then what we're going to have is we're going to end up having we can always express that as a probabilistic mixture of these individual errors. So we can envision like flipping a coin and determining what particular error we end up doing in that coin toss, where the error is going to be described in this form. However, if we have a circuit that can correct any arbitrary error of this form, if we have a probabilistic mixture of them, then the circuit will do just as good of a job correcting a random choice of E1, E2, E3, and E0. So what that ends up meaning is that we can actually use this in order to correct more generic errors. Like, for example, even deleting a quantum bit and replacing it with utter garbage, like a random state. That is something that this code can correct against, which is actually kind of remarkable if you think about it. So that is how quantum error correction ends up working. And what it allows us to do is it allows us to dramatically reduce, as in polynomially reduce, or exponentially in the code distance that we end up using, reducing the probability of seeing errors in quantum systems. And so what this ends up meaning is that by using more and more quantum error correction, we can, in principle, have noisy hardware, provided that the noise on the devices is sufficiently well behaved, and redundantly encode the quantum information in such a way so that we can detect and correct the most common errors that the device is going to see. And so that's the essence of quantum error correction. Obviously, there's a heck of a lot more to the field than just this the Shor code, which I discussed today. In fact, you could spend your entire career looking at more or less nothing but quantum error correction, and continue to have things to do for almost ever. It is an incredibly deep field, and this intro was just designed to give you an idea about why or how quantum error correction works. Because if we didn't have this ability to be able to correct errors in quantum devices, then this would not, all of this quantum computing stuff that I've talked about so far would not be a realistic model of computing. Or a practical model of computing, I should say more accurately. And so this justifies some of the optimism that many of us have, that quantum computers will one day be able to be built using quantum error correction to be able to surmount the control errors and other errors that we run into in trying to engineer large-scale, complicated quantum systems. So that's quantum error correction, and with this, we provided a good enough argument for how quantum computing works, and also why it works and why it's a reasonable model for computing. What we're going to be doing going forward is we're going to actually kind of take a step more into the abstract and start talking about quantum query complexity. And this is going to be useful for allowing us to understand more abstract quantum algorithms that are useful for handling entire classes of problems. And also, it'll allow us to be able to prove separations between the complexities of different quantum algorithms in terms of the number of times that we have to access a quantum subroutine known as a quantum oracle, which ends up providing the salient information that specifies the particular problem. So that's where we're going next. And ultimately, we're going to be building this up to giving you an understanding of how more modern algorithms in this space, such as quantum linear systems algorithm or simulation algorithms, end up working. So thank you very much, and see you all next time.